Okay, everybody. So today we're going to be talking about a couple concepts related to changes in phases of matter. The first one we're going to be talking about is evaporative cooling. Along with that, we're going to talk about the difference between vaporization and evaporation. After that, we're going to talk about the relationship between this thing called vapor pressure and boiling point. So what determines the boiling point is really the vapor pressure of a liquid, and we'll discuss what that is. And then we'll talk about what exactly vapor pressure is and how it's established and what this dynamic equilibrium means. And then finally, we'll talk about how we can change the boiling point of a substance if we change the atmospheric or pressure outside of that substance. And how we're also going to be talking about the difference between normal boiling point and boiling point, those differences as well. So let's get started with that. The first thing, so let me present this. The first thing is evaporative cooling. Well, really, let's talk about the difference between vaporization and evaporation. So when you hear the word evaporation, most people think of a liquid turning to a gas, and that is true. That is true. Same thing with vaporization. Vaporization is when a liquid turns into a gas. Okay? But what's the difference between the two? Well, vaporization is when a liquid turns into a gas at the boiling point. So at the point which vapor pressure equals atmospheric pressure, the liquid turns into a gas, we call that vaporization. Okay? At vaporization, pretty much all the particles have sufficient kinetic energy to turn into a gas, but they just haven't broken the intermolecular forces. They all haven't broken the intermolecular forces to turn into a gas just yet. Some have, but not all have. Okay, so remember that when we did the phase change diagram curve and that flat portion of the graph, right? We have the water heating up, heating up, heating up, and then all of a sudden it goes flat. And that is where vaporization is occurring, where we have enough energy, we have the sufficient kinetic energy, but we just need to break those intermolecular forces. Okay. Now, evaporation is actually when a liquid turns into a gas below the boiling point. Okay, so below the boiling point. So only the molecules on the surface of the liquid have sufficient energy to turn into a gas. Okay, some of those molecules have enough energy to escape the intermolecular forces and turn into a gas. Okay, and why is that? Well, if we look at the Maxwell-Boltzmann distribution curve here, we see that even at low temperatures, there are some molecules that are moving very, very rapidly. Okay, 100K is very, very cold. 300K is very, very cold. Okay, well, actually, I shouldn't say 300K is not very, very cold. 300K is more like a little bit above room temperature. A little bit above room temperature here. So 300K is pretty warm, and there's some molecules that have enough energy, that have a sufficient kinetic energy to turn into the gas phase. But those molecules will only turn into the gas phase when they reach the surface of the liquid. Okay, so the molecules at the surface of the liquid that have this sufficient kinetic energy will escape into the gas phase. Okay, when those high energy particles leave, what happens to the overall average kinetic energy of all the particles? Well, it actually decreases. Okay, if we lose the highest energy particles and then we take the average energy, the average is going to go down. Okay, we remove the highest numbers, the most energetic particles, and the average goes down. And if you recall, the average kinetic energy is the temperature. It's proportional to the temperature. Okay, so if we remove the highest energy particles, we lower the kinetic energy, therefore we lower the temperature. Okay, and that's what we call evaporative cooling. Okay, so evaporative cooling, the high energy particles leaving behind the slower moving energy particles, the average kinetic energy goes down, and we get cooler. Okay, that's why we sweat. That's the reason we sweat. The sweat goes onto our skin. It absorbs energy from our body. The high energy particles leave. The water gets colder on our skin and cools us down. Okay? That's why when you come out of the water, maybe you're swimming in the pool and it feels nice and warm, you're pretty comfortable, but then you get out and the wind hits you. Well, that water is now evaporating off your skin and getting really, really cold. Okay, same thing, evaporative cooling. Now, animals like dogs and cats, they don't sweat. They don't sweat. So what they do instead, they use evaporative cooling too. But what they do instead is they use the water in their lungs. They use the water in their lungs to evaporate. So that's why they pant. When a dog gets really, really hot, he starts panting. And what it's actually doing is evaporating the liquid in their lungs and lowering the temperature of the water in their lungs and cooling them down. If you all have any cats or you ever seen cats, cats actually pant too. I have 2 cats, and when they were little kittens and they would run around a lot, they would pant. But cats are most of the time lazy, so they don't run around enough to pant most of the time to get too hot. And if they get really too hot, they just sleep. So cats don't do it as much as dogs. They don't pant as much as dogs, but panting is what cools cats and dogs down. Okay, so let's talk about this thing called vapor pressure and boiling point. So boiling point is actually the point at which vapor pressure equals atmospheric pressure. We'll talk about what vapor pressure is in the next slide, but just know that boiling point is when vapor pressure equals atmospheric pressure. Okay, now it actually varies with atmospheric pressure. So if the pressure outside changes, the boiling point changes. Okay, so if you increase the pressure, you increase the boiling point. If you decrease pressure, you decrease the boiling point. You'll notice this in, I don't know if anyone here does any cooking or if their parents have a pressure cooker. Pressure cookers use this idea to increase the temperature of water. Okay, because typically if you take a thing of water at sea level and you heat it up and it starts boiling, it will never get above 100 degrees Celsius or 212 Fahrenheit. So it's the boiling point of water. Okay, it'll all boil away to steam before it gets any hotter than 100 degrees Celsius or 212 Fahrenheit. Okay, you can try it at home if you want. Put a thermometer in a boiling water and you'll see it never gets above 100 degrees. Okay. However, if you were to increase the pressure by putting it in a pressure cooker, then that water can get higher than 100 degrees. Okay, and that's why, and it gets hotter than 100 degrees and it cooks things faster. So if anyone here has a pressure cooker, if they make stews or anything like that, a pressure cooker cooks things much, much faster. Increasing the pressure, increasing the boiling point, increasing the temperature at which something boils. Okay. Now, when we say that water has a boiling point of 100 Celsius or 212 Fahrenheit, well, what we're actually referring to is this thing called normal boiling point. The normal boiling point is actually the point at which something boils or turns into a vapor at 1 atm of pressure, or basically at sea level. This is normally what we think of as boiling point. So when someone asks you what's the boiling point, well, this is what you're actually thinking of. Okay, but boiling point changes with pressure, whereas normal boiling point does not. Okay, at boiling, that's where vaporization occurs. And at boiling, you'll see those little bubbles that are forming at the bottom and coming up. That's not air. That's actually water turning to steam. If you watch as the bubbles rise from the bottom to the surface and they pop, you'll see little puffs of steam. Little puffs of steam. And that's actually, the little bubbles are just steam. Okay? So boiling can occur, those vaporization occurs all throughout the liquid when you're at something that's boiling. Okay? In evaporation, the liquid turning to gas only occurs at the surface. It only occurs at the surface. So evaporation only happens at the surface. Boiling, vaporization happens all throughout the substance. Okay, so what is vapor pressure? Well, vapor pressure is the pressure exerted or the force exerted by a gas above a liquid resulting from the vaporization of liquid. So, for example, here we have a container with some water in it, and what's going to happen is these are going to evaporate. And if the container remains open, some of those particles are going to escape. Okay? and they'll keep escaping forever. Okay, now the vapor pressure here and the vapor pressure here are actually pretty much the same. However, the particles are leaving. Okay, so as a particle leaves, another one evaporates. The particle leaves, another one evaporates. The particle leaves, another one evaporates. Okay, so we maintain that vapor pressure through evaporation. Now in a closed container, what happens is the particles will evaporate, and they'll evaporate, and they'll evaporate until they reach the vapor pressure of that liquid. Okay, every liquid has a different vapor pressure. So once it reaches that vapor pressure, then what will happen is it's not going to stop evaporating. What's actually going to happen is it's going to evaporate, and then some of it's going to condense. So for every particle that evaporates, one will condense. One evaporates, one condenses. One evaporates, one condenses. One evaporates, one condenses. One evaporates, one condenses. Okay? And when that's occurring, when we get that where it's like an even exchange, we call that a dynamic equilibrium. Because it's equal, the rates of change are equal, but it's still changing. It's dynamic. Dynamic means changing, right? Dynamic or moving, changing, right? So it's continually just switching, evaporating, condensing, evaporating, condensing. Okay. Now, vapor pressure does not depend on surface area. So the vapor pressure of water in a large container compared to a small container will be the same. It doesn't matter as long as there's liquid there, the vapor pressure is going to be the same. Okay, vapor pressure does not change based on the amount of liquid. As long as there's liquid there, the vapor pressure is going to be consistent. Okay, and last thing here is the vapor pressure and how it's related to boiling point. We just talked about that. If when vapor pressure is equal to atmospheric pressure, then we have something boiling. Okay, so as we increase the temperature of something, we're increasing the vapor pressure because more and more particles are going to evaporate, more and more particles are going to turn into a gas. Okay, so as we increase the vapor pressure, we're getting closer and closer to the boiling point. Once the vapor pressure and the atmospheric pressure are the same, then we get a substance to boil because now the pressure of the gas and the pressure of the atmosphere are the same. So the gas no longer, or the atmosphere no longer pushes the liquid down, back down into the liquid. That liquid is now can escape. Okay, so you have the vapor pressure pushing up, the atmospheric pressure pushing down. Okay, when the atmospheric pressure is greater, it makes the liquid stay a liquid. Some of them escape sometimes, right? But then once the vapor pressure is equal to the atmospheric pressure, now it pushes off the atmospheric pressure and it's free to become a gas. Okay, kind of like pushing off the lid there. All right, and as we increase temperature, we increase vapor pressure. So this is a vapor pressure curve. Increasing temperature, we see increase in vapor pressure. Okay, and when vapor pressure equals atmospheric pressure, we get the boiling point. So each of these vapor pressures will tell you at what temperature that substance will boil. Okay, so 600 millimeters of mercury will boil at about 20 degrees Celsius for diethyl ether. Okay, for water at 600 millimeters of mercury, it will boil at about 95 degrees Celsius. Okay, if we lower the pressure even more, so we lower the pressure to 200, it'll boil at 80 degrees Celsius about. So water will boil about 80 degrees Celsius if we lower it to about 200 or 250. So that's how we're reading these charts here. You notice that as we increase pressure, we increase the temperature at which it boils, so we're increasing the boiling point, and vice versa. If we decrease pressure, we're decreasing the temperature at which something boils. Okay? All right, and that's it. That's all I got. Hopefully that you guys understood that. There is a video with the triple point. If you want to watch that video, feel free to do so. I think it's pretty cool. I'll try and post some more videos about these different topics about boiling point, vapor pressure, so you can watch them again and maybe try and understand a little bit better. All right, see you guys later.